Hi, Chem 101 students, and welcome back for this week's material, which is acids and bases. So I'm going to start by defining what are acids and bases. You have seen them previously when we talked about types of reactions. We talked about neutralization reactions in the past. We'll review that a little bit. We'll also go into much more detail about what acids and bases are. So just a definition here for acid and base. An acid, you've been able to recognize from the chemical formula of an acid in the fact that it has an H in front. And I'll tell you the reason why all these acids have an H in front is because the definition of an acid is a substance that gives up in solution an H+1 ion. And it results in the formation of an ion called hydronium, which has the formula here H3O+1 in water. And we'll talk about how that happens. Bases are defined as H+1 ion acceptors in solution. They generally make hydroxide in water. And so you guys may be familiar, if you remember back when we talked about neutralization reactions, all the bases that we discussed were salts that were rather not salts, but ionic compounds that contained hydroxide in them. And there are other bases that produce hydroxide in water as well. Finally, salts are just another name for ionic compounds that do not have hydroxide, because if they were an ionic compound with hydroxide, we would call them a base instead of a salt. So a salt is just a word for all ionic compounds that are water soluble but don't have hydroxide in them. So acids, bases, and salts, these are referred to as electrolytes. And what electrolyte means is that when you put these substances in solution, they conduct electricity. They basically dissolve in solution to produce ions. And what carries the charge in solution is the presence of the ion, which can carry electrons through the solution as the ions move in the solution. And so you may have wondered before, what? Oh, electrolyte, Gatorade, right? Brondo, Gatorade, it has electrolytes, right? Electrolytes is just a fancy word for acids, bases, or salts. So Gatorade has electrolytes because it's got salt in it, but it sounds fancier when you say electrolyte. So any ionic compound that dissolves in water, or including also acids and bases as well, these will be electrolytes in solution. It's because acids, bases, and salts will produce ions when you put them in water. So the way in which these ions are produced is by what's known as hydrolysis. And so we've discussed hydrolysis in the context of ionic compounds, not as much in terms of acids and bases, but we're going to talk about that now. We're also going to talk about a concept called equilibrium. And we're going to differentiate between what we're going to call strong acids and bases. These are going to be acids and bases that completely separate into ions with none of the ions staying attached to one another. So we say there's no equilibrium for these strong acids or bases, whereas other acids and bases, which we're going to call weak, do not completely separate into ions. Some of their ions stay stuck together. And since they don't completely separate and the reaction doesn't go towards complete separation of ions, we say that they have an equilibrium, because some of the substance separates into ions, but some of it does not. And so at this condition of equilibrium, we have a little bit of both. We have some of the reactant here and some of the product ions as well. I'm going to show you some examples and provide some context here for this idea of equilibrium as we move forward. So first, let's talk about acids. So again, hydrolysis is referring to the production of ions, or the ionization, when these substances are put in water. So an example of an acid here would be HNO3, or nitric acid. Hopefully you remember how to name these. This is still important. It's called nitric acid because it has a nitrate ion in it. So if the negative ion is nitrate, the acid's called nitric acid. And so, as we said, acids are H+1 donors. They give up H+. So if we have nitric acid in water, what's going on is the H plus ion is going to unattach from the nitric acid and go and attach itself to the water. And what this means for the products is that the H plus is no longer attached to the nitrate. So now the nitrate is just a nitrate ion by itself, aqueous, with a -1 charge. And reminder, aqueous means dissolved in water. Now the water has picked up an H plus. So now it has 3 H's, but also the charge is 1 greater. It is 0 for water. It's a neutral molecule. But once an H plus is added, you have an extra H, and the charge is now up by 1 unit, up to +1 from 0, where it was before. And so again, this is indicating that acids, they give H plus, and if they're in water, they can give H plus to water, and they form this H3O plus 1 ion, which is called hydronium ion. And this ion is listed on your sheet of polyatomic ions. We haven't discussed it before because, well, it's relevant when we get to the discussion of acids, which we're doing right now. Now, when it comes to hydrolysis of acids in water, it is possible to write the hydrolysis which includes water and shows explicitly the water getting the H+, or you could choose to not show the water. And both of these are acceptable ways of writing hydrolysis reactions for acids. And so you guys know from back when we were doing nomenclature about acids is that we can recognize this as an acid, nitric acid, because it has an H in the front. And for acids, the H, and when it goes into water, makes the H+1 ion. So we have an H+1 ion as the positive ion here, and that charge is canceled by the -1 charge of the nitrate ion here. And so the difference between these two ways of writing it is here we're showing just the H+1 ion separating from the nitrate ion. So you have these two ions, aqueous, dissolved in water. Whereas in the top version, we include the water and show that the H+ is attaching itself to the water to make a hydronium ion. But either of these ways is okay to write an acid hydrolysis. And often when we talk about aqueous H+1 ions, this is interchangeable with the idea of hydronium ion, because even though it's not explicitly shown here, if you know what hydronium ion is, you know this is aqueous, it's in water. So the H+1 will attach itself to the water molecule and make hydronium. However, in the first version of writing this here, we show directly that the H+ is attaching itself to water. And both of those are acceptable ways of writing hydrolysis for an acid. Now, nitric acid is what we would refer to as a strong acid. And what a strong acid means is that when you put this nitric acid in water, it 100% dissociates, meaning it completely separates into H+1 and nitrate ions. And very, very quickly after you put the HNO3 in water, there's no H+ ions still attached to nitrate ions. They are all separated completely. There are 6 strong acids that you want to know. I have put them in a box here. You want to make sure to have these in your notes for the final exam. What are the strong acids? They include HCl, HBr, and HI. And one way of remembering this is that chlorine, bromine, and iodine are all in group 7 of the periodic table. And so these acids are all strong acids. And then there are 3 strong acids that contain polyatomic ions. They are nitric acid, perchloric acid, and sulfuric acid. Now, if you can't remember how I managed to name those, remember the final is coming up soon, so you may want to go back and review your nomenclature, because that's definitely going to show up on the final exam. Now, another note here is, although I was covering a little bit with my head, all other acids are considered weak. So a weak acid is one that does not 100% dissociate. It may 98% dissociate, or it may 10% dissociate. We only call acids strong when they 100% dissociate. Every other acid dissociates less than 100%, and we call those weak. An example of a weak acid would be acetic acid. So acetic acid has a H plus ion, of course, as the positive ion, and it has an acetate ion as the negative ion. So if we show this in water for the hydrolysis, again, the H plus ion is given away by the acid, because that's what acids do. They give away H plus 1 ion, and it is going to attach itself to the water. So what we have remaining of the acetic acid is just the acetate ion. So you can see it lost the H, and also the charge went down by 1 unit because it lost H plus, meaning essentially the hydrogen left an electron behind. That's what causes this to have the -1 charge. So when you lose the H plus like this, like the acetic acid did, you lose the H, and also your charge goes down by 1 unit from 0 down to -1 here in this case. Now the water is going to gain the H plus, and so you're going to see here the water is H2O with 0 charge, but then once it gains the H plus, it has 3 H's, and also the charge went up by 1 unit from 0 up to +1. And so when you lose the H plus, your charge goes down by 1 unit. When you gain the H plus, your charge goes up by 1 unit. Again, like any acid, it is okay to write it also without the water. One thing I also want you to notice is that here I have used a double arrow for this hydrolysis. You should always use a double arrow for a weak acid hydrolysis like this, and it's because for the weak acid there is an equilibrium. This acetic acid, we can write it in this way as well. It does separate into H plus 1 ions and acetate ions, but not completely. Some of the H plus 1 ions remain stuck to the acetate ions. So we have a double arrow here because once the reaction has gone as far as it's going to go, we still have some reactant left, and we also have some of these products, the H plus 1 ion and the acetate ion. And so since you have some of both, we know that this reaction is going both ways. It's keeping some of the reactant, but also making some product. Many reactions do this, in fact. But for weak acids, you should always write this double arrow. And again, what's happened here is the H plus has separated from the acetate. So we have acetate ion, which is C2H3O2 with a -1 charge, and we have the H plus 1 ion. And of course, we have one of each because +1 cancels charges with -1. So acids are always going to be making H plus 1, or equivalently, we can call this hydronium ion, H3O plus 1. An aqueous H plus ion, as long as you understand chemistry, which you guys do, was interchangeable with a H3O plus 1 ion, or a hydronium ion. So that's what I say here. An aqueous H plus 1 is the same as hydronium. It's just assumed here that if the H plus 1 is aqueous, it is attached to a water molecule, which makes it a hydronium ion. Also, again, the definition of an acid is it's something that gives an H plus 1 ion. When it's in water, that H plus 1 ion attaches to the hydronium. And so saying H plus 1 or saying hydronium is saying the same thing. Now, H plus 1 ion is also often called something else. H plus 1 ion is often called a proton. So that's a word you're going to see me use a lot. Instead of H plus 1 ion, I will say proton because it's easier to say. Why do we call H plus 1 ions protons? Well, it's because a hydrogen atom, not an ion, but a hydrogen atom, which is neutral in charge, has 1 proton and 1 electron. But if you have an H plus 1 ion, that means you have an H atom except you have removed an electron. So whereas an H atom, so an H atom here, H atom is 1 proton and 1 electron, and if it's hydrogen 1, it's got no neutrons. An H plus 1 ion only has the 1 proton because the electron has been, so I'll just use a different color here. The electron is no longer there now for the H plus 1 ion. It was removed because it was forming an H plus 1 ion, which means it lost 1 electron. And so an H plus 1 ion is really just a proton. And so you're going to hear me and other people call H+1 ions protons all the time. These words are used interchangeably as well. Now, properties of acids. So we've seen how you could recognize an acid based on its chemical formula. It has an H in front. But how would you recognize an acid just if you saw one or smelled one, tasted one or something? Acids taste sour. In fact, it's the H+1 ions that taste sour. So protons are detectable by your tongue. A bare proton tastes sour to your tongue. Isn't that interesting? Your tongue is so sensitive that it can detect the presence of individual protons in water. Our bodies are truly amazing in that way. They taste sour. Protons taste sour. They have a taste. It's sour if they're in water. Acids will react with most metals. When I think of this, I always think of the Alien. I don't know if you guys seen the Alien movies, but it drools this like acidic drool on this metal platform in space, and the metal platform goes psh, and starts bubbling while the acid reacts with the metal. Yeah, acids react with metals. There's litmus paper. Oh, you guys aren't going to get to see litmus paper in person this semester, unfortunately, because we're online. But acids turn. There are two types of litmus paper: blue and red. Acids turn blue litmus paper red. They don't change the color of red litmus paper. So red is the acid color for litmus paper. And that's a way that we can detect that a solution is acidic. If you do things with pools, you may have pH or acid base test strips like that too, like litmus paper. Acids will react with metal carbonates to produce carbon dioxide gas. And so this is, for example, if you see the grade school volcano with baking soda and vinegar, that's a reaction of acetic acid, which is vinegar, with sodium bicarbonate, baking soda. And so you end up with a bubbling carbon dioxide gas formed. Finally, acids neutralize bases, and we discussed acid-base neutralization way back in week 4, I believe it was, but we will review that a little bit again in this lecture. So sour foods contain acids, so they're sour because they have acids. For example, acetic acid, vinegar, is sour. Citric acid, which is the acid in lemon juice, lemons and oranges and other citrus fruits. Lemon juice is about 4 to 8% citric acid, for example, which gives it its sour taste. And tartaric acid is the acid found in grapes, which gives them their sour taste. So tartaric acid is a kind of larger organic acid. Whoops. What about bases? So bases also dissociate in water. Again, we're going to have strong bases and weak bases. Strong bases are going to be those that contain hydroxide ions directly in the base. An example is calcium hydroxide here. So if you put calcium hydroxide in water, it makes the one calcium ion and 2 separate hydroxide ions. Note the way we write that. We write a 2 in the front because once the calcium hydroxide is dissolved in water, all of the ions separate and float around independently in water, like we discussed in previous chapters. And so we get 2 separate hydroxide ions. So we write the 2 out in front in this way. And again, calcium hydroxide has 2 hydroxides because each one is -1, so that gives you 2 negative charges, which cancels with the positive 2 charge in the calcium. Notice that no water is written here. So for hydrolysis of strong bases, it doesn't make sense to write water unless it's a weak base. For strong bases, it doesn't make sense because it's going to produce hydroxide directly. What we'll see is that for weak bases, the hydroxide will be produced from the water, so we will have to write the water. But for strong bases, we should not write the water. It only makes the reaction more confusing to look at. So don't add water for strong bases. And they are ionic, so the water only acts as a solvent. It's not reacting, and so we shouldn't write it. Now, there are a number of strong bases. They are all metal hydroxides. So just like for strong acids where it meant 100% dissociation of the ions, For strong bases, it also means 100% dissociation of the ions. And we have these 7 strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide, cesium hydroxide. These all contain group 1 metal ions. Lithium, sodium, potassium, and cesium are all in group 1. Also, calcium, strontium, and barium hydroxide are strong bases. These include calcium, strontium, and barium, which are in group 2 of the periodic table. Beryllium and magnesium are also in group 2 of the periodic table, but they don't make strong bases because beryllium and magnesium hydroxide are not soluble in water, so we don't consider them strong bases for that reason. Now for weak bases, we're only going to talk about one weak base, and that weak base is going to be ammonia. There are lots of other weak bases. Generally, you can recognize them because they have a nitrogen atom in them. Remember, bases are proton acceptors. That's the definition. So when it comes to the strong bases, the proton acceptor is going to be the hydroxide. If it accepts a proton, that produces water. But in the case of a weak base, the weak base here is the proton acceptor, and we have to write the water because the water is going to behave as the acid in relationship to the weak base here. The water is going to give away an H+. So the H+ is going to go from the water to the ammonia. And so the result is going to be that the ammonia is going to pick up an H. So you see in the result here, we have 4 H's instead of 3. But also note, it's not getting an H atom, it's getting an H+1 ion. So the charge goes up by 1 unit from 0 up to +1. Likewise, water is losing H+. And so it has now 1 less H as a product, and also the charge goes down by 1 unit from 0 down to -1. And so what we have left here, after the water loses an H+, what we have left is the hydroxide ion, OH-1. Okay, now remember, for acids, when we wrote the hydrolysis equation, we could either include water or not include water for both weak or strong acids. But for strong bases, we have to not include water. For weak bases, we must include the water because the water is where the H+ is going to come from. So we need to show the water to show that it's the H+ is being donated from the water and being accepted by the weak base, ammonia here. Notice we also have a double arrow because this is a weak base, meaning there is an equilibrium here. Some of these ammonia molecules will accept an H+ and make ammonia, but not all of them. There will still be some NH3 left over. So we have a double arrow here because we're going to have an equilibrium, meaning when the reaction stops going, there's going to be some of these reactants, some ammonia still left. But there's also going to be some products. As opposed to this top one for strong bases, this 100% ionizes. When you put the calcium hydroxide in water, there's no calcium hydroxide left after it dissolves. So that's why we write a one-way arrow, because we only have products for the strong base hydrolysis. But for the weak base hydrolysis, we will have an equilibrium, meaning that we will have some of the ammonia still remaining, but we will also have ammonium ion and hydroxide ion produced. Remember that the definition of a base is it's an H+1 acceptor. So with the weak base here, ammonia, it's accepting the H+ directly. But for the hydroxide bases, it will be the hydroxide that accepts the H+. When it does, that makes water. Bases always make hydroxide ion in some way. If it's a strong base like this one, it makes hydroxide ion by directly producing it when the ions separate in water. If it's a weak base, it makes hydroxide ions by accepting the H+ from water, and when it does, that produces hydroxide ion. So how will you recognize a base? Well, if you feel a base, bases will feel slippery on your skin. Lots of cleaning products are bases. They feel slippery. And for very strong bases or concentrated bases, what's going on is that it is reacting with the oils that are in your skin cells and turning them into soap, and the soap washes away with water. So the reason why bases feel slippery is because it's actually turning your skin into soap, which is then washing away, and that can cause burns if it's very concentrated. For example, Drano is pretty concentrated sodium hydroxide. So if you got that on your fingers, you would feel it slippery, and you wouldn't want to keep it on your hands. It would eat at your skin. It would react with your skin to turn it into soap, and then it would wash away. If you're tasting bases, they taste bitter. So some examples of bases in foods would be like coffee sometimes tastes bitter. It also tastes sour. It has both some acids and bases in it. Beer, especially hoppy beers, hops in beers taste bitter because they have weak bases in them. Blue is the color of litmus paper when it is exposed to base. So red litmus paper will turn blue. Blue litmus paper will remain blue. Bases neutralize acids. Again, we've talked about acid-base neutralization, but we will review it momentarily. And finally, though, we're going to talk about salts. So again, salts are just ionic compounds that do not contain hydroxide and are soluble in water. So calcium nitrate, for example, is an ionic compound that is soluble in water and does not contain hydroxide. So it is a salt. And when ionic compounds dissolve in water, as we discussed in the solutions chapter and in previous chapters, it produces two ions. It produces separate ions here. The calcium ion is separate and it has a positive 2 charge. And the 2 nitrate ions become separate from one another. So notice we write the 2 out here in the products, 2 separate nitrate ions. When it's in calcium nitrate, they're all the ions are stuck together in chunk. But once they separate into water, you get 2 separate nitrate ions and a calcium ion. All the ions are separated and floating around in water by themselves. You don't add water for salts. They're ionic. The water is just a solvent. It doesn't react. So it doesn't make sense to add the water for salt. We just say it's aqueous, meaning these are dissolved in water. Another example here is ammonium chloride, another ionic compound that does not contain hydroxide. It's a salt. So it produces ammonium ion +1 and chloride ion -1. Remember, watch out for ammonium. That's our only positive ion that we talk about in this class that is not a metal. It's a polyatomic positive ion. So remember that polyatomic ions such as nitrate or ammonia stay as a unit together. When it comes to salts, a salt again is defined as any ionic compound that does not contain hydroxide. Because if it contained hydroxide, it would be called a base instead. If an ionic compound is soluble in water, it will completely dissociate to produce ions. We've talked about that in the past. And salts can actually produce acidic, basic, or neutral solutions, depending on what ions are present in the salt. And so salts can actually produce acidic, basic, or neutral solutions as well. Now, what about concentration? So in the solutions chapter, we talked about the concentrations of various things, and we use the concentration unit molarity, or moles of solute per liter of solution. Now, often we're going to be interested in the concentration of hydronium ions or hydroxide ions that are in solution, because that's going to tell us how acidic or basic a solution is. So when calcium hydroxide, for example, dissolves in water, if we want to know what the concentration of the hydroxide ions are, we're going to have to figure out how much hydroxide was produced from the hydrolysis of calcium hydroxide. So remember, calcium hydroxide, the ions separate here, and every 1 mole of calcium hydroxide is going to produce 2 moles of hydroxide ions. So if the concentration of calcium hydroxide is 1.56 molar, well, that means 1.56 moles per liter. That means per liter of water, it will produce 1.56 moles of calcium ions, but it will produce twice as many hydroxide ions. So if we want the concentration of hydroxide, we're going to have to take that concentration that we have for calcium hydroxide and multiply it by 2, because 1 calcium hydroxide is going to produce 2 hydroxide ions. So the concentration of hydroxide ions here is 2 times 1.56 molars, or 3.12 molar of hydroxide ions. And this is exactly because, again, if we have 1 liter of water, that's going to contain 1.56 moles of calcium hydroxide. But when that separates into ions, that will produce that same amount of calcium ions, but it will produce twice as many hydroxide ions. So our concentration of hydroxide ions is twice that amount, 2 times 1.56 molar in this case. Neutralization. So for neutralization, I'm going to show you a slide that I've shown you in the past when we talked about types of reactions. So we talked about precipitation reactions, gas evolution reactions, and neutralization reactions. And a neutralization reaction is defined as a reaction where you have an acid and a base, and they react and produce a salt and water. So the acid, you'll recognize the acid again because it has an H in the front. That's how you recognize acids from their chemical formulas. And you'll recognize the base because it will contain a hydroxide in it, like sodium hydroxide here. And so remember, when we're deciding what's going to happen here in a neutralization, we're going to do our good old double switch, So remember the double switch. Hopefully you remember that. I'll ask you to do it again on the final exam. So this is a good review of the good old double switch. We have to identify what ions are composing each of these. So in the base here, it's composed of a potassium ion, which is +1, because it's in group 1 of the periodic table. And then for the negative ion here, it's the hydroxide ion. Okay, and the positive ion here is the H+ ion, and there are 2 of them, but that's not what matters to us. Remember, first we're trying to identify what ions are in these. We can worry about making sure we have the right number of everything later. And then finally we have SO4. So here you'd have to remember what polyatomic ion that must be. So hopefully you still have those memorized. This will be the sulfate ion, SO4 2-. And so we're going to do our double switch here. The potassium is going to go with the sulfate, and the H+ is going to go with the OH-. And so now we want to write the products here. So one of our products will contain H+ and OH-. So H+ is +1, OH- is -1, so we just need one of each. And so this makes HOH, or also known as H2O. And that is liquid. Put an L there. It's the bulk liquid, because these are aqueous, even though it's not written here. These are aqueous. Okay. And now the other product is going to be composed of K+1 ions and sulfate ions. Now remember, we got to make sure that the charges cancel. We've got one positive, but we got 2 negatives, but only one positive. So we're going to need another K+ in here. That will give us 2 positives to go with our 2 negatives. So when we write the formula, it's going to be K2SO4. And this is going to be aqueous. It's soluble in water due to the group 1 ion. Now remember that what I wrote at the top is just my work. It's not the answer, okay? The answer is this right here. Of course, we can take out the question mark too. So this is the answer. This up here is the work. Don't show me your work on the answer line, because these are now neutral ionic compounds now that the ions have all come together. So it's not appropriate to write charges like right here or right here. What we want to do last is we want to make sure we balance this. So when we're balancing it here, you'll notice we have 2 potassiums on the right side. So we're going to want a 2 here. So we have 2 potassiums on the left side, 2 times 1. And then we got 2 oxygens on this side, besides the ones in the sulfate. So for sulfate, we have one sulfate here and one sulfate. All right, that's good. Well, we've got two more oxygens here, so if we want to have two oxygens, we'll have to put a 2 right here. That will give us 2 oxygens, 2 times 1. And 4 hydrogens, 2 times 2. And here we have 4 hydrogens, 2 times 1 here, plus 1 times 2 here. And so now our equation is balanced. And so, again, we identified the ions, positive K plus 1 on the base, sulfate on the minus, H plus and the hydroxide make our water, and ultimately we get potassium sulfate and water. And it doesn't matter which one you write first or second. Again, I wrote water first here, here I wrote water second. They both mean the same thing. Remember that the charges have to equal 0. If you write KSO4, that's not right. It's K2SO4 because you need 2 potassiums to cancel the charge with the sulfate. Ultimately, we balance the potassiums by balancing the reactions, but we don't do that until the very end, after we're absolutely sure we have written the correct substances here. And so that was a little review of how to do neutralization reactions. And make sure to review that in our chapter about types of chemical reactions that we had previously as we get closer to the final. But this was a part of that, what we talked about before. So why do you care about acid and base? Maybe you're going to be a nurse. Why do you care about learning about acid and base? Actually, there's lots of good reason why people would want to know about acids and bases, even if they're not going to be chemists. One reason is that antacids that we take to neutralize our stomach acid is about it's about 0.1 molar hydrochloric acid, HCl. And sometimes the stomach produces too much acid, so people take antacids which have like magnesium hydroxide or aluminum hydroxide in them in order to neutralize the acid. These are delivered in the form of a suspension so that they're not completely dissolved in water. So that's why they taste like chalky, and you have to shake them before you use them, because magnesium and hydroxide and aluminum hydroxide are not very soluble in water. But you shake up the Mylanta or whatever, and then you drink, an ounce of it or whatever to neutralize the acid. And it may contain magnesium hydroxide, aluminum hydroxide. Some contain carbonates or bicarbonates instead. Finally, let's talk about the concept of conjugate acid-base pairs. So let's define conjugate base and conjugate acid first. A conjugate base of a substance is what remains of an acid after it loses an H+ ion. And a conjugate acid is the opposite, what remains of a base when it gains an H+1 ion. So the difference between a conjugate acid and a conjugate base is 1 proton, 1 H+ ion. So, for example, here again, we've got nitric acid, or nitrous acid, because this is a nitrite ion, right? So this is a nitrite ion. So the acid with the nitrite ion is called nitrous acid. Hopefully you remember that acid-base nomenclature from before. And so here, this is a weak acid again, so we've got a double arrow here. It's not nitric acid with which is a strong acid. It's nitrous acid, which is a weak acid. And when it behaves as an acid, what happens is that it gives up a proton, the H+, and the water gets it, because that's what acids do. They give up protons. And so the H+1 ion attaches to the water, so it now has 3 H's, and the charge goes up by 1 unit from 0 up to +1. The nitrous acid lost the H+, so the H is no longer there in that product, and the charge has gone down by 1 unit from 0 down to -1. So in this reaction, the nitrous acid is the acid, and the nitrate is its conjugate base. It is what you get when it loses 1 proton. When the nitrous acid loses 1 proton, you get its conjugate base, nitrite ion. Notice the difference, it's 1 proton. HNO2 has 1 more proton than NO2 minus. See, it has an H and the charge is 1 higher. Nitrite ion has one less proton than nitrous acid. There's no H here, the H is gone, and the charge has gone down by 1 unit. So the difference between an acid and its conjugate base is an H and 1 unit of charge, okay? Now, also in this reaction, the water behaved like a base. The water was the base, and it gained an H+. So this was its conjugate acid of the water. And so we would call these a conjugate acid-base pair. So the ones that are red are a conjugate acid-base pair. That's another way we say this. They differ by 1 proton. Water and hydronium are also a conjugate acid-base pair. They differ by 1 proton. The H3O+ has 1 more proton than the base water here. So that's why it's called the conjugate acid of water. It's what you get when you add 1 more proton to water. And you can see it has 1 extra H, and the charge has gone up by 1 unit, up to +1, because it has 1 extra H+ on it. So HNO2 is an acid. If it gives away H+1, it forms its conjugate base, nitrite. Again, the difference is 1 H+. The nitrite has 1 less H+ than nitrous acid. Water is amphoteric. What we're going to see is water can function as either an acid or a base. In this case, it's behaving as a base. So the word amphoteric means a substance that can behave as either an acid or a base. Water is like this. So in the case of this reaction, water is behaving like a base, meaning it is accepting a proton. And when it does, water accepts the proton, so it is a base, right? Since it's accepting a proton, it's a base. When it gains the H+, it forms its conjugate acid, which is H3O+. Again, the conjugate acid is what you get if you add 1 H+ to a substance. So here we've had 1 H+ to water. So we have 3 H's, and the charge is up by 1 unit from 0 up to +1. And so H3O+ is the conjugate acid of water. And another way we say this is these are a conjugate acid-base pair, because water is also the conjugate base of H3O+. It's what you get if you remove a proton from H3O+. And nitrous acid is a conjugate acid of nitrite ion. It's what you get if you add 1 H+ to nitrite ion. So we would say nitrous acid and nitrite ion are a conjugate acid-base pair. And water and hydronium are also a conjugate acid-base pair. Okay. So we say, yeah, here's what I just said here. HNO2 and NO2- are a conjugate acid-base pair, because if you subtract a proton, -1 proton, you get the conjugate base nitrous acid, and then if you add 1 proton, you get its conjugate acid, HNO2. So we say that they're a conjugate acid-base pair, meaning they differ by 1 H+1 ion. Nitrite ion has 1 less than HNO2, and HNO2 has 1 more proton than nitrite ion. Hydronium and water are also a conjugate acid-base pair. Hydronium has 1 more proton than water. Water has 1 less proton than hydronium. So if this one loses one, again, if this one loses 1 proton, so if hydronium loses -1 proton, then you get its conjugate base, water. And if water gains 1 proton, then you get the conjugate acid of water, which is hydronium. These differ by 1 proton, therefore they are a conjugate acid-base pair. So a question I am definitely going to ask you on the quiz this week and on the final is, I'll give you a substance like HF, and I'll ask you, what is the conjugate base of HF? Well, conjugate base means what you have if you have 1 less H+. And so if you have HF here, and you remove the H+, well then all you've got left is F, the H is no longer there, and the charge goes down by 1. HF has 0 charge. We don't usually write 0 charge. But when you lose an H+, your charge goes down by 1 unit. So the conjugate base of HF is the fluoride ion. What is the conjugate acid of carbonate ion? The conjugate acid of carbonate ion will be what you have if the carbonate gains 1 H+. So conjugate acid means 1 more H+ on it. So the conjugate acid, if you add an H+, well, it's going to have an H now in CO3, and the charge will go up by 1 unit from -2 up to -1. You don't have to write the 1, of course, but so they differ by 1 proton. The bicarbonate has 1 more proton than carbonate, so you have 1 H and the charge is 1 higher from -2 up to -1. So here's the kind of question I can ask you again. What is the conjugate base of H3PO4? Well, that's going to have 1 less proton, because the conjugate base, remember, this means 1 less proton. That's what conjugate base means, 1 less proton. And so this is going to have now only 2 hydrogens, and also the charge will be 1 less. It will no longer be 0, it will be -1. What is the conjugate base of HNO3? It's what you have again if you have 1 less H+. So the H will no longer be there, it will be just NO3, and the charge will be decreased by 1 unit because it lost the H+. So from 0 down to -1. Here's another question. What is the conjugate acid? The conjugate acid of an NH3+. This means 1 more H+. So the conjugate acid of ammonia is going to have not 3 hydrogens, it will have 4, because it'll have 1 more, and also the charge will be 1 unit higher. Not 0, but 1 unit higher, +1. Finally, what is the conjugate acid of HBr? Again, conjugate acid, or sorry, what's the conjugate acid of bromide ion, Br-1? Again, the conjugate acid has 1 more H+. So there's going to be a H here on the Br, and the charge will go up by 1 unit from -1 up to 0. So we don't write the charge 0. Don't forget about 0. 0 charge is a thing. A lot of the times my students will skip from -1 all the way up to +1, but that's 2 units higher, not 1. If you go 1 unit higher from -1, that's 0. Not +1, that would be jumping 2 units, right? So it's neutral HBr with no charge, so we don't write any charge there. And so that is it for the introduction to acids and bases. So what we covered in this lecture is the definitions of acids and bases, also the way to write hydrolysis equations for weak acid and strong acid, weak base and strong base. We also discussed what are the strong acids, what are the strong bases. We reviewed neutralization reactions, and also finally we talked about the concept of conjugate acids and bases. For our next lecture, we're going to go into the idea of pH, which is a convenient way of expressing the concentration of hydronium and hydroxide ions in solution. I'll see you in that next lecture.